So in the previous video, we saw a straight edge only method to actually allow us to draw a line in any direction through a point that we know lie on a conic. We're given 5 points, so we know that there's a unique conic associated with these 5 points, which we don't have, by the way, but the previous method allowed us to define a line through any of these points and effectively compute, and I'm going to do this here using GeoGebra's facility, but effectively locate, and let's see if GeoGebra allows me to do this intersection over here, right? So you don't need a conic at all, you just have a method to locate that intersection. Okay, very good. Now let me talk to you guys about a property. So what we're trying to do in this video is actually locate this point here, which we're going to call O. Let's call this point O, and that's the center of the conic. Okay. Now here's how we're going to proceed, simply using the previous method as a subroutine. Okay. I'm going to do the following. First of all, let's talk about a property of all ellipses, or all conics, in fact, and they have to do with something called conjugate diameters. All right. Now let's take a segment or a chord that connects, for example, P1 to P5, any two of these 5 points. So this is a chord, right? Actually, instead of drawing it as an infinite line, I'm going to draw it as a segment. Let's draw it as a segment because I want it to be a chord, a proper internal chord. So here's a chord of this ellipse. Let's make this guy be green. And again, guys, I'm going to get to O without ever touching the continuous curve, okay, that GeoGebra is here, is drawing for me on the screen. Now let me show you first of all the basic strategy for us to get to O. Okay, we're going to draw a chord, so far so good, and we're going to identify with ruler and compass the midpoint of this chord. Okay, so there's the midpoint of this chord. Now let's now draw a parallel to this line, through any one of the other 3 points on the ellipse. So just using GeoGebra's facility, but we can do this with a ruler. We're going to draw a parallel to this line, passing through any other point. For example, P4. Okay, there it is. Now I'm going to be using the previous methodology to identify. So let's take P4 now as my starting point. I have a direction here, and using my previous algorithm, I have a way to actually, just with a straight edge, locating this particular point. Because I have 5 points on an ellipse, I've chosen a direction, and in this case here, it happens to be parallel to P1, P5. I'm starting from a point, so I should be able to locate the intersection with the green curve, which I don't possess, using the previous method. I'm not going to do it here because it involves a few operations, so it's just going to pollute this video, but I really encourage you guys to do this as an exercise. So now, if I can locate that point, I can think of this segment here as also having a midpoint, which I can locate. Oops, to do that I actually have to draw a segment. So let's draw this segment between P4 and this point that was just located. And by the way, let's call this point here, just so that it is mnemonic, I'm going to call it P4 prime, okay, which I've located using my previous method. Okay, and when I do that, I can now turn off this line and just focus on the segment. Now this segment too has a midpoint. Now a well-known fact about ellipses is that parallel chords, the midpoints through parallel chords, and they're known as conjugate gradients. All the midpoints, they are on a line, they are collinear. Okay, all midpoints of parallel lines through an ellipse are collinear, and the line that goes through them passes through the origin. Okay, so imagine I'm going to do this. I'm going to choose P1 and P5, draw a line, identify its midpoint. This is the first midpoint of a conjugate diameter. Then I'm going to take another point out of my 5, choose a direction through it which is parallel to that first one, and then using the previous method identify P4 prime, and then locate this chord and locate its midpoint. Now I can connect these two guys, right? Very good. So let's, so I still don't know where O is, right? Because let's hide O. Where is O? I just know now that O lies on this line, but I don't know where O is. Okay, so to actually locate the point on this line where O lies, I need to repeat this construction a second time. So let's do this. I'm going to continue to use P1, and I'm now going to connect P1 to, for example, P4 over here. And since this is intrinsic to the 5 points I have, I'm going to go ahead and, again, color this as I did before. This is the second diameter, which itself is going to have a midpoint. So let's go ahead and locate its midpoint. So its midpoint is over here. Okay, and now I need to find another conjugate diameter parallel to this one. Okay, so I'm going to take a parallel line from this one, and I'm going to make it pass through any other of the points that I've so far used. It could be P5 that are still available, right? When I say any other point, it cannot be P1 or P4 because I'm going to get the same line. So I need to move away. And I do have a selection here. I actually can use P5, P2, P3, or I could use P4, which is also on the ellipse, and it's a new point. It wouldn't hurt to use P4 prime. But just to make it simpler and more canonical, I'm going to use this guy over here, P5, to reduce the number of points that I'm consuming in the ellipse, right? Now again, let's go back to our method. I have a point on the ellipse, P5, and I have 5 other points on the ellipse. In this case here, I already have 6, right? 1, 2, 3, 4, 5. So there's 6 points on the ellipse now. But I have 1 point here. I only need 4 more. And what I'm trying to do is I'm trying to locate the intersection of an arbitrary line through this point with the green curve. How do I do that? I use my previous method. So after I apply those steps, that previous method is going to return to me this point over here. Okay, so now again I can consider this segment from, let's call this point here, let's give it a name, let's call this guy P5 prime. P5 prime over here. Okay, so I'm going to construct P5 prime the same way I constructed P4 prime. Okay, now once I construct that, now I have this chord, which is not this way, but it is this way. Let's go ahead and draw a segment between these two, and let's hide this line. Okay, so now I have the second chord. This chord is parallel to this P1, P4 segment, and let's go ahead and identify its midpoint. Here we go. I've identified its midpoint. Again, now I have 2 parallel conjugate diameters through which I can draw a line, and that line will also pass through the center of my ellipse. Now we're done because I have 2 lines now that are guaranteed to pass through the center of the ellipse. I can simply intersect them and say, well, this point must be the center of the ellipse. Let's go ahead and check that using GeoGebra's estimation where that center is, and you can see that it's right there. So again, we have a method that only uses a straight edge and a compass. I think we might need a compass to identify the midpoint of these segments. Okay, but it's still a sort of 3,000-year-old. I'm only using 3,000-year-old instruments, 5,000 perhaps. And I was given P1, P2, P3, P4, P5. I was not given the continuous curve, the conic. By the way, this conic could be a hyperbola or a parabola, and this would work all the same, right? And all I did here is I started from this first conjugate gradient between 2 points that are known to be on the conic. Then I drew a parallel through another point to be known to be on the conic, P4. Then using the previous method, I got to P4 prime. Then I got the 2 midpoints. Let's color this guy here as red. Okay. So I got the midpoint of red, which I'm also going to color red. Okay. And I ran a line through the midpoint of my first chord, and they're parallel. So that line here, this first line here, okay, must pass through the center of the conic. Then I repeated the procedure by now choosing another line, another chord between 2 known points, for example, P1, P4. I drew a parallel through another known point on the conic. I had many to choose from, and I drew this line here through P5, and using the previous method, I located P5, the intersection, with a conic. Okay, then I drew this, and then I got its midpoint and the midpoint of the chord, the corresponding parallel chord, and I ran a second line through it, and these two intersect at the center of the conic. So you can see that this is pretty robust. I can move any of these points, okay, and I can robustly identify where the center of the conic is. Here's the example with a hyperbola. I can always go to a hyperbola. So this thing is pretty robust. Modulo collinearities, if you have too many points that are collinear, this thing breaks down. So for example, P3, P4, P5 should not be collinear, because then the conic becomes degenerate, and then O goes to infinity. So you don't want that. You want what we call general position sets of 5 points. So there you have it. The intersection of midpoints, of lines through midpoints of pairs of conjugate diameters intersect at the center of a conic. Okay, in the next video, I'm going to show you a method to locate, so perhaps the most beautiful one, to locate or specify the axes of the conic. And once you do that, you can easily compute the foci. Okay, so I'll see you on the next video.